So, hello everyone. We will learn about the next step in our analysis of 90-degree bend pipe. We will basically solve the meshes that I had done in my previous video. But before that, we are going to look at this paper. This paper says numerical study on flow separation in 90-degree bend pipe under high Reynolds number under K epsilon modeling. So this is actually the same study we are doing now actually. It's a 90-degree bend pipe and under high Reynolds number. And the modeling they have followed is K epsilon modeling. So we will try to follow this paper, what the methodology they have used in this paper, and try to match our result with this curve. If our data matches this curve, then we can say that our validation study is all right. Okay. Uh, so let's start. But before that, I want to show you something about this paper. Let's see here the diameter we had chosen in our paper, in our study. It was 0.5 in the long direction and 0.2 in the shorter direction. So as I use the diameter of 0.01, thus I had chosen 0.05 according to 50D, and I chose 0.2 according to this 20D. Anyhow, uh, so before going on to that, we are going to see some aspects of this 90-degree bend pipe. Uh, let's see if we study this validation. At the very beginning of our study, our model and simulation setup are first validated against the existing experimental and numerical data in reference. So here the curvature ratio is 2, and what does this curvature ratio means? This curvature ratio means actually divided the RC divided by the D. The D is this, and the RC is the coordinate system distance to the center of this cross section. So that must be 2. In our case, it is also 2. Uh, in our case, this distance from this distance is 0.02, and the diameter of this is 0.01. So the ratio would be 2 as well. So the curvature ratio matches here. And at the next, the Reynolds number is 6.10 to the power 4. We don't really need to match this actually. We just, if we specify this model, this K epsilon model, as you can see here, the let me locate it. This K epsilon model, it will automatically generate a transient case in our study. So we do not need to follow this actually. Follow this Reynolds number here. It will automatically select this. And next is, if we see here in this author's study, they had a mesh content quality of 2.85 million hexahedron elements. In our case, we did not use hexahedron elements, we used tetrahedrons. So our mesh will be a bit bit bad than this mesh elements. Uh, Always remember, the hexahedron elements are the most perfect mesh elements used in any study. So the authors also use this hexahedron mesh elements, and they got total number of 2.85 million. That's a very good number of mesh. And they also say that the y plus value is 30 to 90. Is nothing but the ANSYS studies that is performed on the wall actually. Actually, these videos are really out of the scope. Uh, these concepts are really out of the scope of this video. So I'll not explain this actually. So let's get on to our study first. So I have written down the steps for the sake of simplicity. So you can follow the steps accordingly. So take a screenshot if you want. And now we will move to the modeling. As the mesh study will be done in the Fluent, so let's drag Fluent here. But before dragging the Fluent, I need to update this mesh actually. So let's just open the mesh file. Even if you did not change anything in the mesh, you still have to update the mesh before importing into the Fluent. So just for that, I'm just opening the mesh file, and after updating that, I will generate the Fluent. Well, my setup is has become really slow. It takes time to open the mesh file. Here is our mesh file. All right. So let's now impose the Fluent. First, locate the Fluent. Here you go, and drag it here. So before doing that, let us see. Now I have to update the mesh. The app.sign is on the mesh box. So go to the mesh file and go for update. And update. Wait until a message in this box appear. There should be a message for the Fluent being ready for the mesh being ready for the Fluent. Let's check here. Yes, the mesh transition to Fluent was successful. Now we can run the setup, and it will open your Fluent app. Before starting the Fluent, use double precision and increase your solver processes to 4 and start. As this file is opening, as this Fluent is opening, it might show not responding, but wait a bit. Feel free to skip or forward for 5 seconds or 10 seconds here, as these processes are very slow. It will take some more time. Feel free to go forward 5 seconds or 10 seconds. It is reading the mesh, and it is done. Okay. So first, what we will change is the model here. As in our paper, in the paper here, they also use the K epsilon turbulence model. See, so we also will use this K epsilon turbulence model in our case to get same result as this result. So let's change the model. Double click on the model, change it to viscous SST K omega. Double click on the model as well and change it to K epsilon. Our case here is as well the K epsilon, not the K omega, but K epsilon. And change it to realizable and choose enhanced wall treatment and okay. Now change the materials, go for fluid, double click on the fluid And now we have to change the density and the viscosity according to this paper actually. According to this paper, the this is the air actually. I need to use the water. The water having is 990.2 kg per meter cube and the viscosity of 0.0006. So we'll change according to this. So the density we will change it to 990.2 and the viscosity should 0.0006. Let me check again. 990.2 and 0.0006 and okay, and click change and create and then close. Now what we're gonna do, change the boundary conditions of the inlet only. Double click on the inlet. It will take some time to open the page for the inlet. And here you go. And just change the velocity magnitude to 6. Velocity magnitude doesn't matter. We can change it to match the graph, but let's say the velocity magnitude is 6 and apply and close it. And then go to the monitors, expand this and go to residuals and change these values to a very low value. Enter. OK, and then cross and go there again to easily change the others. And now change this value to all of these values. Just copy paste this value to all of these values. So let me copy and paste. And OK. And now let's do the calculation. Before running calculation, let's initialize our problem and do the hybrid initialization and initialize. It will also take some time. Feel free to skip 5 or 10 seconds. We will be trying to match this case data. So all of that with what I just selected in my Fluent was from this paper actually. You can also see the name of this paper and search for it. And mainly we will take the Kim data, the Kim et al. Data. I have the paper for the Kim as well. These are his data. The study is the same. It's also 90-degree bend pipe flow induced by 90-degree elbow in turbulent pipe flow. We will mainly compare his data. Let me show you the graph. This data. The data here is a bit very condensed, so we will take this data. Let's look at our Fluent if it is done or not. It is still initializing. Pressure information is not available. Alright, it can be done. There will be a message in this box that the initialization is done. Before that, we have to wait. And the initialization is done. So now we will run calculations. A bit problem, it is not responding. Your setup quality is very important in this type of work. Wait a bit, feel free to skip for 10 seconds. Okay, so go to the run calculation, double click on it, and change the number of iteration to 1000. We won't need this 1000 iteration because the model we have used, the KH7 model, it will very reduce the iteration number. And calculate. And before running the calculation, I should have changed the time scale factor. It will reduce the time. I cannot change it now. Anyhow, we have to wait. Feel free to skip again. Let's stop this solution and change the time scale a bit. Change your time scale to 5 and then calculate. Now wait a bit until you see the graphs become linear. Feel free to skip again here. And the solution is beginning. And you can see the graph now. The graph looks fine, but only 3 iterations has been done. So we need at least 30 to 40 iterations. Now, in the meantime, let me explain what y plus, what in this paper the y plus means. We had seen the y plus, the value of non-dimensional distance from wall is strictly controlled using standard wall treatment function, y plus, for a near wall cell used in the present study. And what does y plus means? In the axis simulation, y represents the vertical or secondary axis in a Cartesian coordinate system. It actually means the distance from the mesh, from the wall of your mesh. Y, uh, let me break it down a bit. It is a kind of a non-dimensional wall distance used to evaluate how well the mesh near the wall, near the wall of a geometry is captured during the turbulent flow simulation. Actually, it is crucial for accurately modeling the fluid behavior near the solid surfaces. And I just tried to briefly explain what y plus means. You can look it up in the Google if you want. Let's look at our Fluent file right now. I guess I have gotten a good value, good lines. But still, let it run a bit. You adjust the iteration number 13. It's very soon to close the iteration right now. It's taking quite much time, 3 minutes. Alright, this video is getting too long. I will start the next video with the detailed result after it had reached at least 30 to 40 iterations.